All right, so looking at our announcements, reminders coming up. One, you have a mastering assignment due tonight, which you can do. We're definitely going to cover all the materials and homework by the first half of class. You have a group quiz on Friday, and then your first exam is a week from today. Yay! I don't call it celebration of learning because that's weird. It's not really a celebration for anybody. But it's definitely your test. And I will let you know, not all, what chapter are we in? 14. Not all of 14 will make it onto the first test. We'll have to have some carryover 14 to the next test. So I'll let you know Friday what the cutoff is, so that you have the weekend to get started. Then Monday, we'll do a little material and then a little bit of review. And as you're looking forward to the test, maybe not enjoyment-wise, but like scheduling-wise, looking forward, the practice exam is already on my website. If you want to start working on it this weekend, it's already up there. You can start looking at what kind of questions will be on the test. Questions about any of that? All right, we'll do a little recap and then we'll move on. All right, so first order reaction, right, is where we have the rate equals the rate constant, concentration of A raised to the first power. The integrated rate law is this. All right, this is our integrated rate law, and it's written in such a way that we can then graph it just first order. So first order has that equation and that graph along with it. So since that's only true for first order, we should look to see what happens when it's a second order reaction. All right, so this is a second order reaction, right, for that same reaction. Now I'm saying it's second order in A, so rate equals rate constant A squared, referring to second order. The integrated rate law for second order reactions is given here. That's the one I prefer. It's the same as this one, it's just rearranged. Right, it's the exact same equation, just two different ways of writing it. One has all the A's on one side, and the other one, the reason I prefer the one that is boxed is because if I write it that way, I can make a graph. So if I write it that way, I am in the business here. We'll get started, right? We definitely have to have that. So if my second order rate equation is written that way, what goes on the y-axis? Yeah, 1 over A. Then what should I put on the x-axis? Yeah, time. What variable tells me about slope? K, and is K a positive or a negative in this case? Positive, so does the slope go up to the right or down to the right? It's going to go up. I realize it shouldn't be like this. It shouldn't be right at the 0. Alright, so this has a slope equal to K. Then the last point on my graph will be right here, not 0, but really close to 0. The y-intercept is the y-intercept is 1 over the initial concentration. All right, so if we look at the difference between a first order and a second order graph, what is something that is the same on both these graphs? They're both linear. What else is similar? They both have slopes. Are they in the same direction? No. Right, they're both equal to K, but in a first order, it's downward slope. In a second order, it's an upward slope. What's another thing that is the same between these two? time, right? The x-axis on both of these is time. But then different is this is 1 over a for a second order and the natural log of a. So if I was going to give you a graph, well, there's a good chance I might do this. Give you a picture of a graph and say, is this a first order graph or a second order graph? You should be able to tell me which one it is. Okay? You can write that down and star it. Be able to identify first order versus second order graph and pull the important information out of it, right? If I give you a graph with all the numbers on it, you should be able to tell me K, you should be able to tell me the original concentration, stuff like that, okay? Alright, let's see what we have next. Alright, let's say we now have an example problem. I need to find my notes. There we go. Alright, so this is an example. Actually, you know what? I want to do a first order example first. Will that throw everybody off if I do an example before this example? Everybody's okay with that? Okay, let me do that. Alright, so we'll do a first order example, because the one I have in the PowerPoint is a second order. So we'll do the first order one first. Alright, that was funny to me. That's fine. Let's see. What if we have Alright, so let's say I'm given this equation, dinitrogen pentoxide, and it decomposes to nitrogen trioxide and nitrogen dioxide. I tell you it's a first order decomposition product. And the reaction has a rate constant of 7.8 times 10 to the negative third inverse seconds. And the N2O5 has an initial concentration of 1 molar. I'm looking for how much N2O5 is left after, we'll take 125 seconds. Alright, so I know how much I started with. I know it's first order. I want to figure out how much do I have left after this time has elapsed. So we need to use the first order rate equation, which was this one. Alright, so which of these things am I looking for? What is the thing that is missing? We know the time, 125. What else do we know? Am I looking for this A or this number 1A or number 2A? I'm looking for this one, right? Because I told you the initial concentration was 1. So we can plug this in, right? Negative K. So we're going to do negative 7.8 times 10 to the negative third inverse seconds. The time was 125 25 seconds plus ln Alright, so using these equations, once you know which one to use, it's pretty straightforward. You just plug it in. You solve for whatever I'm asking for. Let me Let's see. Well, things cancel out. Let me go to -8, third, 5. What's the tricky thing about the natural log of 1? It's 0, so I try to make it real easy. So it's just equal to the same thing. Alright, this is now equal to that. How do I get bracket A all by itself? Raise it to the E. What? Raise it to E. No? No? That's what I think, but I'm like, oh, raise it up to the E. No, Justin. Yes. Yep. I don't put them in here because you can't take the natural log of a unit, but using your scientific intuition, we're looking for concentrations, and so it's going to be the same concentration units as what you started with. Yeah, natural log rules for units are real funky, but yeah. Because now these cancel out. So then bracket A equals whatever that is. Little e that. It takes into account that already. That's what this K is doing. It's subtracting, sort of, or ratioing. That'd be a different question. Like, this is how much is remaining. If I asked how much was used up, it'd be the difference. But I can't imagine I would ask that. No, I will not ask. I'll ask other trickier things. Yeah. Yes. Yep. So little e and ln are opposite, so they cancel out. 10 to the is the opposite of log. So if you see an log, you got to do 10 caret. E and natural log go together. Yeah. Feeling good? Feeling good about that? Alright, in that case, let's go to the second order example. And oh, I'm giving it away. Woo, that's so exciting. We're not there yet. That was just very exciting. I'm very excited with that next one. Alright. Alright, so let's do a second order practice problem, and then we'll practice interpreting some graphs. Alright, let's say I have ammonium cyanate, which in water rearranges to give urea. The rate equation for this process is given, rate equals K. If it's a 2, what should that immediately in your head be? Second order, right? Second order. And I have a K value given. So, in this case, I gave you the original concentration of 0.229 molar, and I gave you the final concentration. So what thing am I looking for? Time, right? I'm looking for time in this case. So, first thing, see if I can get it all on the screen at once. Because it's second order, from here, we have to use the second order rate equation. So now, which variable am I looking for? T, right? I'm looking for T. So we can plug in everything else we know. Which molarity goes in the A0? Yep, 229. And then this one goes in the A. We're going to do 1 over 0.180. Whoop. Okay. K, 0.0113. Looking for T. Over. That T looks like a plus. Alright, what is a great first step to solve this kind of problem? 2 options. I can see it going either way. You can subtract your fractions. So either you can solve the fraction and subtract the decimals, or you can just subtract the fraction. Either way. Right. So I'm going to do it all in one step. I'm going to make them in the decimals and subtract them. I'm keeping the units of K around because we'll have to figure out what my time units need to be. Alright, so now what's my final step? Alright, get the T by itself. Just divide through. So 1.18 divided by 0.1.3. Alright, this is a meaningless number unless I have units with it, right? So how did I measure my time for this particular experiment? In minutes, right? Because it's inverse minutes right there. This must be 104 minutes. Everything else canceled out because this was really 1 over m. 1 over m, so this is inverse molar. And then they'll cancel out with that. Only if I asked you to. Which on a test seems unlikely because I have to ask you to do so many other things that you converting minutes to seconds is not that's not the skill I'm concerned about. It may be a bad assumption on my part, but I'm assuming you could probably convert minutes to seconds and be fine with that. I mean, I've been proven wrong before, right? So, alright, how do you feel about first order and second order plugging it in and solving for it? Okay. Let's say I did an experiment. Alright, so I did an experiment in my head. I didn't actually do this. But I looked at how sucrose breaks down in the presence of water to glucose and fructose, which have the same formula, just one's a 6-member ring, one's a 5-member ring. Talk about that later. Super fascinating, sugar chemistry. But anyway, so what I did is I plotted the data, right? So here's my, I did different times, different concentrations of glucose, and I measured the rate. So I looked at natural log of rate and 1 over natural log concentration, 1 over concentration, and I plotted the graphs from that, right? So this is natural log because it's first order, this is 1 over because it's second order. What do I look at to figure out which is the best fitting line? Do I look at the equational line or the r squared? R squared, right? R squared tells me what? If it was 1, what would r squared be telling me? It's a perfect fit, right? Every single dot is on your line. If it's an r squared that's 0, it means you are a crappy scientist and you should probably start over because it means there's no correlation. Looking at my 2 graphs, which one is the better fitting data? The first one, right? So it's most likely a first order reaction? The answer to this is a first order reaction. Alright, so now I know it's a first order reaction based on my graph. How do I figure out what, I call it calculate K, but how do I find K from this graph up here? It is the slope. So where do I look to find the slope? The equation of the line. There's only two numbers in the equation. Is it the first number or the second number? First number. So K equals, do I include the negative sign? No. Negative just tells me it's going downward. K's, remember K, always, 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 always positive. No such thing as a negative K. So K in this case is just equal to 0.0037. What would that be? Inverse minutes. Alright, so now we want to figure out what is the concentration of sucrose after 175 minutes has elapsed. Alright, so what we need to do is get myself some more paper to write on. Alright, so if it's the first order equation, Yeah. I mean, actively learn them. Spend so much time with them that they're second nature. I think that's actually what I meant. But yeah. You'll have to be able to, if I say it's first order, you have to give me the equation, or if I give you the graph, be able to pull the data out of it. Whatever that means to you. Alright, so I am looking for the concentration of sucrose after 175 minutes. Based on the information, so we are which variable are we looking for? ln of A or ln of A0? ln of A, alright, we know K, it's right there. We know T, right, so I'm asking after 175 minutes. Where would you go to find A0? A bunch of different options. You could either look at the y-intercept and take and undo the natural log of that, right, because ln of A0 is this number. Or you could go to the table of original data I gave you, and this is the original concentration. Both of which are true. Your option. I'm going to go with the one with the least mass. I'm going to use this. Yep. At time 0 is 0.316. Yes. Yep. So I'm looking for this. Negative. You're given that. And my original concentration of A was 0.31. Alright, so then it's just plugging it all in. Ballpark saying how many specific figures carries out. most people get that. Alright, questions about first order, second order. Graph, tables, calculations. The first order graph? Oh, on here. Yep. Yeah, okay. Okay, good. Alright, in that case, let's talk about the only other kind of rate reaction that we're going to be concerned with in here. Called a zero order reaction, or zeroth order reaction, I guess. You put TH with an O. I think that's right, zeroth. This is where rate equals K, A raised to the exponent 0, right? Raised to the power 0. What is a simplified way to write that? Yeah. Alright, so the integrated rate equation for a zeroth order reaction is this. Or why would I prefer the second choice? I can graph it! Yay! Who doesn't love a good graph in the morning? You guys may not appreciate it after all these graphs, but there's nothing more pleasing than a nice graph that has a linear line, r equals 1. Alright, so again, time goes on the x-axis, so you can't tell the graph based on the x-axis. It's going to be based on the y-axis. What should I put on my y-axis in this case? Alright, just plain A. Which direction should my slope go? Down or up? Down. And again, slope equals K. And then what's my y-intercept equal? Just my original concentration. So the main difference is just going to be this y-axis. The y-axis is going to tell you if it's first, second, or zero order. Right? If it's first, it's natural log. If it's second, it's 1 over. If it's zero, it just is. It's just concentration. Alright, so here, this is, I think it's from your book, but this is like an all-in-one, one-stop shop. The order, the rate equation, the integrated rate law, what the plot should look like, what the slope is, and what the units are of K. Okay, I'm not going to spend a bunch of time on it. Just star this in your notes that this is a useful table to kind of double check yourself on. Or print off this one slide and walk around with it in your pocket. When you're thinking about it, you're like, wait a minute, I have it in my pocket. Let me look. No? I don't have pockets today, so obviously I can't carry it with me. Like, I like skirts, but it bothers me that there's never any pockets in them. Obviously, only a problem for like a half the population here. Unless you're a kilt wearer, in which case that could, I guess, be an issue. Alright, so that leads us to the fascinating conversation of half-lives. So, right, talking about all these different orders of reactions, it was given 175 minutes, how much is left? That's kind of somewhere in between, right? You know how much you put in at the beginning. Most often you want to know approximately how long until it's half done. Right, 50% of the reaction has completed. How long does that take? Because then you can extrapolate and figure out how much farther to go till the end or whatnot. So, half-lives, often referred to as T subscript 1/2. is the time required for half of a reactant to be consumed. And we're going to look at in terms of first order reactions. All right, so our first order rate law. Is that, right? So I'm specifically looking for this half T time, right? I'm looking for the T required for half the reaction to be over. So if I know the initial concentration is 50 moles, what concentration must it be at half over? 25, right? You took this concentration and divided it in your head by half. So it'd be the same as saying if half the reactant is consumed, you're at half the original. That's the concentration you're looking for. Let's say I wanted to simplify this equation. What is one thing I can now do to simplify this? Right, over here I had A and A0. I couldn't do anything. Now I have A0s on both sides. Right, so I'm going to get the A0s all to, I'm going to choose the left. Alright, does anyone off the top of their head remember what fun thing, used loosely, okay, fun, used loosely, thing you can do when you have a subtraction of natural log? Yes, you can factor it. Same thing as division. It's the same thing as saying this. So natural log subtraction is the same thing as natural log division. What can I now cross off? A0's gone. Alright, if I'm looking for the time required for this to happen, I want the time by itself, right? That's the thing I'm solving for. So I'm just going to rearrange this equation. And let me see what that is. Natural. Right, I could put the negative sign next to K. But now this natural log of 1/2 is a constant, or it's just a number. And so the negative of the natural log of 1/2 is 0.693 over K. Which means for a first order reaction, it doesn't matter how much you started with. It just depends on K. Right, I've crossed off all the dependence of the concentration. Question first. Oh, the natural log of 1/2 is negative 0.69. That's just a negative to negative. So it disappears, cancels out, goes away. Whatever the right math word is for that. I don't know. Someone more math oriented can tell me, do negatives cancel out? Do they? I don't know what you call it. So guess what? You have a brand new, super exciting equation. Go ahead and box that. You're going to need that. So, brand new, super exciting equation. We better give it a test drive. Make sure we know how it works. Alright. Oh, and here is obviously a graph that shows how half-lives work. Right, so if I'm at 1 half-life, 2 half-lives, 3 half-lives, farther out, less concentration. Yeah. Yeah. Alright, so let's say I have the rate equation for this reaction for the decomposition that produces the same equation we had like 5 minutes ago. It's the exact same problem we had. Where'd that go? Oh, there it is. Less exciting if I can't find it. It's the same question we had here. We have NO2, N2O5 decomposing, first order. I just rewrote it in a slightly different way, just to give you different options of how you might see it. I'm still saying rate equals K1, right? So first order. So if I give you K, first thing is I want to figure out what is the half-life. How long does it take for half of my reactants to disappear? So we're going to use the equation we just discovered. And K is given. So I just take 0.693 divided by K, and I get, let's see, using 6, I get 1.4 times. What units does my time have? Seconds, right? So that's how long it takes to go from 100% of A to 50% of A. That's all the equation does, right? It's not super complicated. They give you K and you plug in K. So how can I make it more complicated? What if I don't want to know about 50%? What if I want to know about 1/10? Excellent question. Well, right, we can't use this one because this one talks about 1/2. But we're going to walk through it and think through it, and by the end you're like, oh, that was easy. Maybe. Alright, so let's go back to the original integrated rate law. Right, so going back to that. When I said I wanted to go from 50 moles of this to 50%, right, you either divide it by half or multiply by 0.5, whatever it is. What if I say now I have 50 moles of this? What is 1/10 of it? 5, right? You took that number divided by 10. So you can do the same thing. Alright, so if we do the same sort of algebra manipulation, we subtract this over here. A subtraction is really a division. Alright, so just skipping the middle step that we did earlier. Question? Yeah, I mean, you could certainly write T 1/10 if you wanted to keep it straight in your head. That's fine. It's just T1/2 is like a standard notation. T1/10 doesn't show up very often. So, you certainly could. Alright, so now my A0s cancel out. Alright, what else do I know that I can plug in right now? K, right? K is still a constant. I'm just going to go ahead and plug that in. Now you just need to solve for T. Figure out the natural log of that, and divide by that. Make sure everybody gets the same answer I do. Oops, here we go. Alright, so then let's think about if that makes sense. So the half-life was, what was that, 1.4 and 1/3 seconds. Right, so that's for 50% of it to disappear. Did it take more or less time to get down to just a tenth of it? Is this a bigger number or a smaller number? Bigger, right? Bigger number. Good. Alright, maybe I've blown your mind and like you're short-circuiting. Alright, this number is a bigger number, which makes sense. It takes a longer time to get to the point where it's not just 50% left, it's only 10% left of your product. Alright. Let me see what I got left. Alright, I only have one slide left for today, and then we'll pick up Friday on a slightly different topic. And we're not gonna do any practice problems. I'm just gonna go ahead and give you the equations. Alright, that's all great if you have a first order equation, which really in chemistry, the only half-lives we're really concerned about deal with first order reactions. Second order and zero order or more in the biochemical biology range. Chemistry, just about everything we're concerned about is first order, like radioactive decomposition, things like that, ozone falling apart, first order. These two fall into mostly biochemistry range, so we're not going to derive them or do any practice problems with them. I'm just going to give you the final T1/2 equation, and then we'll look at it in context a little bit later. Yeah. Oh, yes. There we go. So for a second order reaction, that is the half-life equation. And what's the biggest difference in this half-life equation versus a first order? Concentration is still important. So in the first order, it just depends on the rate constant. In a second order, because it's this factor of 2 up here, it doesn't cancel out nicely anymore. And so it still depends on the initial concentration. For a zero order, we have that equation. The original, wherever you started with. Oh, sorry. No. It makes it really, really tricky. No, not that tricky. So I'm not going to do any practice problems with those, just you have them, and we'll come back to them later. We'll stop there, because we're going to talk about what makes a reaction occur or not occur. Yeah. Oh, big concept questions for Friday. Alright, so we'll do a quiz on Friday, and it'll be everything through what we just did since the last quiz. So what we covered Monday, today.